So fertility is that capacity the soil has to supply nutrients in adequate amount without toxic substances. So basically, when the soil is highly productive, we actually know that it is fertile. But generally, a fertile soil may not be always highly productive because of environmental conditions, either diseases or supply of water. Because the availability of water is very, very important, especially to allow movement of nutrients and uptake by the plant. So application of water through irrigation is one of the means of improving the fertility and the productivity of the soil. So, as I said, we have those essential elements, that is carbon, hydrogen, oxygen, and a number of macronutrients which are required in big quantities, but also the micronutrients which are required in small quantities. But we also have the non-essential, which are really required very, very minimum quantities. Soil fertility can be lost, and you lose it in several ways. We lose it through harvest of crops. We lose it the way we manage the weeds. We lose it through erosion. We can also lose it through the way the tillage is done. So basically, when we grow plants, these plants need these nutrients, so they mine some of these nutrients from the soil and they take them in their biomass. So once we remove the biomass and we take away from the garden, we basically also lose the nutrients from these soils. And soils being more of friction systems, if you have lost 2 kilograms of nitrogen, you may need more than that to actually put back the 2 kilograms of nitrogen. In terms of weeds and crops generally are in competition, and especially when the nutrient levels are very low, the competition for this scarce nutrient now becomes very stiff, and in some time the weeds grow faster and they starve the crop. So if you remove the weeds without leaving them rot on the soil, then you don't put back the nutrients, and that will be one way of losing the nutrients. Erosion, of course, we know erosion is very selective and is basically target the finest particles in soil, and those finest particles have the highest particle density or surface area, and the fact that they have the highest surface area, it actually means those particles have the highest interaction with the nutrients, so the highest concentration of nutrients. So if those particles are removed, then certainly you are losing a big amount of the nutrients. And in most of our soils, erosion is rampant and generally beyond the tolerable values, meaning that with time we actually lose very fast the status of the fertility fertility of our soil. Nutrients can also be lost through leaching, and particularly those one which can be dissolved into water, especially nitrogen. Through erosion, we lose more phosphorus because of the bound between phosphorus and the soil particles. But through leaching, we may actually lose a lot of nitrogen because of it can be dissolved easily into the soil. But we also have cases where nitrogen can actually be lost in gaseous form, especially when you have those conversion from one form to another. So generally, soil fertility depends on several things. And here, I'm basically looking at four different elements here. One is the soil type. Different soil types have different inherent fertility because of the nutrient they have, because of their characteristics, both let's say physical, biological, and the chemical content. But also the issue of drainage, the issue of texture, the issue of topography, which is linked to water availability, the issue of the depth of the soil, all those will actually affect in one way or the other the inherent or potential and even productivity at a particular time. The other factor we need to consider here is the way the land is managed. Certainly, poor management will actually contribute to reduce crop yield. But we also have pests and diseases. These pests, which are rampant in most of our gardens, contribute to the loss of productivity. And the other factor, which is also very important, is the climate. Here you look at all the different parameters of climate, solar radiation, rainfall, temperature, all and relative humidity are very important in actually either maintaining the water level or losing the water through evapotranspiration. But at ecosystem level, we need to look at productivity with a different eye. And this case here is one of the indicators of productivity is what is above the ground. So it's basically the biomass, the quantity of biomass which we get on top of the soil. And this is a function of the energy budget. The amount of energy, the net energy which is actually received by the ecosystem and which is converted into biomass. So for every ecosystem, we can actually define the net primary productivity or the net primary production, which is actually the global primary production minus the energy used by primary producers for respiration. So NPP is in terms of biomass per unit area per year. So at a given time, the NPP is basically the amount of new biomass which is added during that time. And we need to note that only the NPP is available to consumers. Ecosystem vary greatly in NPP across the earth. So, how do we estimate soil productivity? There are different methods. There are those direct methods, but we also have indirect methods. So the direct methods can be done in the field, can be done in greenhouses. We can do evaluation using in the lab, using some form of experiment under given climatic and management conditions. But the indirect methods also exist, and we can actually use a number of models which have been developed across the world to make an estimate of soil productivity. And for this case, we opted to actually use existing models. There are a number of models which have been developed in the 70s and which have been improved over time. And here I'm thinking about the modified soil productivity index and the land productivity index. So the modified soil productivity index is basically the product of the different factor rating. Okay, so I was starting discussing the estimation of soil productivity. And as I said, we basically used the existing models, and that's what I'm going to discuss now. So we are looking at the models which are developed in the 70s and the beginning of the 80s, and that is the modified soil productivity index and the land productivity index. One is expressed as a product of the factor rating of productivity indicators, and the other one is expressed as the square root of factor rating, the square root of the product of factor rating used in productivity estimation or productivity indicators. So there are several parameters which are used in those models, and that is cation exchange capacity, soil depth, base saturation, the organic matter, slope, texture, drainage, gravel. And there are a number of parameters which can be put in the estimation. And for each of those parameters, they have factor rating. So we actually use a number of those parameters and the proposed factor rating in the model. That is for soil productivity. On the other side, we have to look at vegetative biomass, the amount of biomass generated by a crop. So there are different ways also of making an estimation of it. the first approach could be to use allometry or allometric equation to estimate how much biomass is actually standing and below the ground. Generally, the allometric equation known are using power functions or log functions. And basically, those are the once you transform the power function, you can get some kind of linear function using log. Several of these models have been developed across the world and for different regions. And they use plant characteristics such as the DBH or the height to determine biomass. The second approach is the multi-scale estimation. In this case, measurements are done at a small scale, and then extrapolation is done as the scale increases. I just give an example. If you have done some measurement on plot level, maybe a 40 by 50 or 50 by 50 meter plot, and you have gone and measured height and DBH for those plots, and you want to now extrapolate beyond a hectare and for the entire ecosystem. In that case, you may actually need to develop an allometric equation. Yeah, I was discussing the different approaches to estimate vegetative biomass, and I was saying measurement can be done at a small scale and extrapolated to a larger scale. Of course, if you have done on a 50 by 50 meter plot and you want to do it for a hill slope or a catchment level, then you need to have some allometric equation done, and of course some earth observation information on either the biomass, no, either the DBH or the height of the trees at that scale. So the accuracy of the model is again off. So the accuracy of the model will depend on the data which has been collected at plot level. But of course, the estimation at a larger scale will also depend on the accuracy of the model, but also the size of the area where you want to make an extrapolation. So this raises, of course, the issue of representation of the plots before the extrapolation is done. Are the plots used in estimation of the development of the allometric equation representative of the area where the estimation is going to be done? So basically, you find that the error propagates across scale. So, and that's why accurate measurement should actually be done at the source. But we can also use geostatistics, and geostatistics has turned out to be one of the important tool, especially for regional variables. Regional variables standing for variables which change with position. And this will not require too much of a distribution function as classical statistics will need. Of course, limitation of geostatistics are known, and the user of geostatistics should be aware of it and make sure that some of those limitations are actually taken care of before they are used for estimation of values. The other approach is basically remote sensing. So vegetation is easily, or let's say the indicators of vegetation in remote sensing are known, and one of them being the normalized difference vegetation index. And this can be computed from each of the different satellite sources data we have. And the good thing that some of these images are now available and accessible by most of us. Of course, each of these approaches has its own limitation and strength. Of course, if we do the observation, the direct observations, then we minimize the error. But again, this depends on the tool we have. We can't, and the area we want to cover. We are very limited in actually moving in space if we have to use our legs to actually carry and get the information. Sometimes this information is required in a short period of time. So in that case, you really need remote sensing and all other Earth observation systems to actually collect some of this information. Of course, the issue of geostatistics is known. As I said before, different models will produce different values. But again, the way the data is collected and the requirement on the data is also very important. On the side of remote sensing and other tool, of course, the resolution is also very, very crucial. As I said, the normalized difference vegetation index is the most important indicator for vegetation. And as we know, it is computed based on the red window and the near infrared bands. And this is one of the polarization index used in simple physics, where the NDVI is the near infrared minus the red over the sum of both infrared, near infrared, and the red. This fraction ranges between -1 and 1. And we know the higher the value of the NDVI, the more it indicates the presence of vegetation. So different models have been developed across the world to test NDVI, and the biomass. So some of these are linear functions, others are logarithmic, of course, quasi-linear functions, exponential, which are also once transformed linear functions. And the NDVI and biomass have been strongly related or strongly correlated. And this is very, very important information to actually show that there is some good relationship between the NDVI and the biomass. Of course, there are cases, for example, where the vegetation has grown and the NDVI start going down, but while the biomass almost remain constant. But those are fewer cases when for the forest or the trees have reached maturity. But generally, there is a very strong relationship between biomass and the normalized difference vegetation index. Now, for this case, of course, after this introduction on the concept of fertility and productivity and assessment of land productivity, we went ahead to test some existing model based on the information available. So we collected a number of information on land use, land cover, digital elevation models, soil data, climate data, but also some satellite images, and but also the protected areas. So this data set was important to try to evaluate the different existing models and see which model could actually be used or which type of adjustment could actually be used or done to make sure that we can assess productivity of the land in terms of soil productivity, but also above ground productivity. So this is a sketch of our conceptual model and the way the different models were generated.
Okay, so our conceptual model is the one I've presented there, and this model basically consider, if you look at on the left, two basic models: above ground productivity index, but also the soil productivity index. I will come back to this. It was assumed that the two could have actually conferred to us a land productivity model. But if you look at the above ground productivity, we are looking at the NDVI as an indicator of the biomass, but also rainfall as somehow also associated with the productivity of biomass, but also the land use. So the first thing was basically to make sure that the NDVI was detrended to remove the effect of rainfall, but also the rainfall was used to make an estimation of erosion. So once the NDVI was detrended from the rainfall, we actually had something we could use to actually develop above ground productivity index using normal statistics, classical statistics. Now, for the soil productivity was developed based on fertility potential of the soil, but we also took into consideration the section of erosion. Erosion, which is linked to a number of factors, rainfall with its erosivity, land use cover with a C factor, soil with its erodibility, but also the slope, which generate for us the slope length factor. So if you combine the four factors, erosivity, C factor, erodibility, but also the slope length factor, then you have the potential soil loss. And this potential soil loss was added on the soil productivity index, which was generated based on the existing models and fertility potential to have an idea of the actual productivity of the given soil. Of course, consideration was also done on the environment, basically the human factor, looking at population density, but also the existing cities, because anyway, both population in cities, where we have cities, that's why we expect to have a bit of high concentration of human beings. So that information was supposed to be linked to the land productivity model, basically after the two major indices were fusion to give an average indication of what could be the productivity. But I'll come back to this as we move. So the soil productivity index was defined based on the FAO soil classification. But also we used the model, the best model, to actually also infer, based on the properties of the soil, what was the productivity for that particular soil. So basically, everything was based on the two models, as I said, which were generated between the 70s and 80s, the modified soil productivity index, land productivity index, but we also try to modify some of these models to bring in some kind of clustering or productivity, but also try to look at what the mean factor rating could actually give in terms of productivity index. So this is an example of the modified soil productivity index, where we have the product of the factor rating, then the land productivity index, which was the square root of the product of the factor rating, and then the way we define a cluster productivity being a sum of the different factor rating normalized based on the minimum value and the maximum values of factors we had obtained. And what we had called the mean soil productivity index, which was actually giving us which was computed as the sum of the mean of the different factor rating. So what we use for available properties were basically the cation exchange capacity, the soil depth, base saturation and pH, organic matter, slope, texture, and drainage. So we had in total 7 factors used in this estimation. So the soil productivity was standardized, and then we reclassified it using the FAO factor rating scheme, which show that less than 20 was very low productivity, 30 low productivity, less than 50 moderate, high productivity was less than 75, and above 75 was categorized as high, very high productivity. So we try to compute the accuracy of our model based on the classification from the FAO. And what we actually observed, if you can look at it, so the land productivity index gave us the highest relative accuracy and the overall relatively low errors of omissions, but also fairly comparable errors of commission with other models. But the strength was basically the accuracy and the error of omission. So we also, as I said, estimated soil loss using, since this was done for East Africa, and we use more equations for erosivity, more used different precipitation values, and demonstrated that erosivity could actually be used, generated based on rainfall. And that's the equation he developed for erosivity under the revised universal soil loss equation. So for erodibility, for us to estimate erodibility, we basically used values proposed by Morgan in his publication in 1995 based on texture and organic matter. So we also use Moore et al. 1991 to determine the slope length in QGIS. And the C factors, we borrowed the values from Panagos et al. 2015. Some of these values of Panagos, though developed for Europe, were very, very comparable to values which have been used in different models in East Africa. So those were the different values. And if you look at them with what is known for East Africa, certainly you will see a very good correspondence with what is used in most of our publications. So then we use the FAO 1990 to make a classification of the soil loss from very low to very high, taking less than 2 tons per hectare per year being very low, and above 90 tons per hectare per year as very high. One of the other thing also which was considered here is the annual nutrient input, because this is very important in defining the acquired fertility. So it was necessary that we actually see what is actually going on in terms of nutrient input to see if somehow these additional nutrients could actually affect the actual observed productivity. So what we actually saw is that in most of the countries, addition of nutrients was very, very low to the recommended in East African region, which actually ran between 125 to 250 kilograms per hectare per year for the essential macronutrients. The only country where there are some kind of relatively good, let's say, input of nutrient is basically Kenya and Rwanda. But in most countries, the input was just negligible. Though 31 compared to 250 kilograms per hectare also sound negligible. For the estimation of the net productivity, we used the adjusted vegetation index, soil adjusted vegetation index for 2001 to 2019 to determine the status of land productivity. So as we said, we established the relation between survey and rainfall, and we made sure that the rainfall effect was removed from the survey, and then use the survey to generate the different percentiles and compute the different levels of productivity. So we came up with 8 classes, and these actually are defined and described in the table we have here. So extremely low net productivity for us means these are portions of land that are entirely bare or rocky. And very high, these are portions of land with very high standing biomass, which were close vegetation, close over evergreen or deciduous forest, mosaic vegetation, or grassland or shrubland or forest, or sometimes some kind of cropland with forest. So we had a number of assumptions in generating these models. The first assumption is that vegetation, of course, is very key indicator of land productivity. So if a soil is of very low productivity, then even if the condition remain the same, then the biomass should be very low. This, if a soil is very low to low productivity, then if we see very big biomass, it actually means we have in front of us either a forest or a plantation natural regeneration. So those are the things we are looking for, and we actually cross-check with our estimates. Then for soil of medium productivity, to have high to very high biomass, that means generally there is an intervention which was made. And if soil with high productivity, we see low to medium productivity, it actually means somehow these particular soils have undergone degradation. So those were the major assumption which we have made on our model, the model which was generated. So basically, this gives an indication of what was done. I will actually ask the moderator, and if there are any questions, we are ready to answer them. Otherwise, I would like to say thank you for listening to us, and we are on standby for any clarification or comment or any other question. Thank you very much.
Hello. Thank you very much, Professor, for taking us through that introductory part of the land productivity and assessment and methodology. It was a highly scientific but elaborate presentation. Participants, you'll agree with me that he was down on earth. He took time to make sure that everybody moves with him. Thank you very much, Professor. Going by what the team leader, GMEA South Africa, RCM already said, that this training is two-way. It is sharing and learning. So now I want to invite, if there are any questions, if there is anything to share from you, dear participants, or from any person logged in. So please raise your hand if you can. And if you cannot, you still can chat. You can put it in the chat. Professor or, you know, he's looking at the chat, and anything that comes through, you'll be able to address it. But I'm requesting that maybe we pick 5 at a time. Prof, please guide us.
No problem.
Yeah, no. Let's pick 5 at a time, and then we do what? And then Professor will address them accordingly. Yes, I can see Brian. Brian, please unmute and submit.
Okay, yes, thank you. Brian. Yeah, thank you, Margaret. Thank you, Prof, for the really nice and interesting presentation. So a quick one, I wanted you to comment on the inputs. Don't you think that the inputs are affected by the current nutrient content that these countries have, and that some countries feel that their soils have low nutrients, that actually their input is very high compared to the others that feel maybe their nutrients are considerable enough for the productivity that they want for that particular period? Then do you think these inputs can end up leading to loss of fertility?
Okay. Okay, maybe, Chair, can I maybe react on what the question of Brian?
Yeah, there is another one in the chat, Prof.
I've seen, yeah.
Okay, that's okay. Yeah. You can address those ones in the meantime.
Yeah, yes, let me address those ones. Okay, I think Mekonnen from Ethiopia can be assured he will get the PowerPoint because he was asking for the PowerPoint. Then Fabien is asking what can we say about the impact of climate change issues vis-a-vis the soil fertility and productivity. What we can, of course, climate being part of the factors influencing productivity, we expect, it's anticipated that any change in climate parameters will certainly have an effect on productivity. Some cases, it will be negative depending on the way the climate parameters, the trend of climate parameters, but in some other cases may be positive, as many models or climate models and suitability studies have shown. And this productivity, of course, will vary from one crop to another, because that's another thing someone has to bear in mind. A soil can be less productive for coffee, but it may be good, very highly productive for maize, because productivity may also be crop specific. So as the climate parameter vary, they may favor certain crop and actually be have negative effects on other crops based on the requirement of each of them. Now, going back to the question of Brian, we also suspected that, of course, countries which feel like their soils are relatively exhausted, they may want to actually put more. I think that's the case of Kenya and probably the case of Rwanda because of a number of issues, as you said, the need to increase productivity based on the use of the land. But in other countries, including Uganda, for example, where I think Brian is coming from, there are many people who are actually challenged with their soils, but they don't have resources to actually buy the fertilizer and put. And sometimes they may even not know what type of fertilizer they may have to put. And other cases may actually be that some of these people have negative perception of fertilizer because they have used either adulterated or fertilizer which are not adequate to the crop, or misuse it, and they didn't get an adequate response of fertilization. But it may be true for some countries, as Brian said. So I'm still there to wait for any other question.
Yeah, thank you very much, Prof, for addressing those two. And for your information, dear participants, our professor's presentation has been recorded and will be shared with you. Even others that would like to get it, we shall provide a link to it, and that will be available. So, can we take up another set of questions?
Yes, Chair. I've got 2 more questions. Actually,
yes.
3 more questions. Let me answer them.
Okay.
From Okau, Patricia.
Okay.
She said, what assumption did you use for the effect of temperature to the fertility? I didn't see it anywhere. Thank you very much, Patricia. Of course, it didn't turn out to be in the model, but temperature is a part of evapotranspiration, and we know that the more biomass, the more evapotranspiration. So in one way or the other, temperature is already taken care of in the biomass. This other question is from Tuizere, and the question read, I have a question about fertility and productivity. You have said more, okay, indicators. What about the soil erosion for readability, mitigation, and rehabilitation? I think this natural fertilizer can help the people. Okay, I think probably what you want to say is that if we manage to enhance, to control erodibility, meaning actually adding more organic matter, and then we have relatively very good bounds between particles, then we control erosion, and that could be one way or the other of improving productivity. If that's the question, the way the question reads, then I agree with you that investment towards carbon sequestration and carbon capitalization in the soil is very, very important in improving fertility, and especially due to the fact that carbon and soil organic matter is basically a very big reservoir for most of the nutrients. So improving carbon content is very, very important in improving fertility and productivity of the soil. Now, the other question is from Samuel Equalu, and he said, you cited land use practices as also a contributing factor to soil productivity, but from my side, it's a broader factor. Probably there is need to cite which kind of land use practices contribute highest to loss addition and soil productivity. Yes, Samuel, is fine. You may actually be right to some extent, but we are looking at, in this case here, the above ground productivity. If someone look at, if you put two land uses, example, you put a cultivated land with purely maize, and on the other side, you put, on the same soil, you put trees, any type of trees, but which can grow very fast, and you get your earth observation tool. Of course, you will see that where you planted trees, you seem to be having more above ground productivity. And that's what we are talking about. In this case here, we are not looking at the soil productivity, and that's why you need to, as we discussed in our assumptions, the way we see, we interpret values of productivity, of net productivity, to infer soil productivity. So that's very, very important for someone to understand before you go into interpretation of the values. So another question is from Anthony Kagaro. He said, can you comment on productivity of rangeland as an ecosystem? What challenges are related to this particular ecosystem? Yeah, rangeland are very special ecosystems, especially because of the dropout from the animals, which actually contribute to building some good of carbon and soil carbon or soil organic matter in the soil. But the biggest challenge, of course, of rangeland these days is that most cases try to reduce as much as possible the trees and the shrubs, and basically try to look at what is palatable for the animals. So by so doing, of course, one way or the other, you build on one side the soil organic matter, and the argument will be, oh yeah, but soil, it is easy actually to store more in the soil. But the biggest challenge for rangeland is that most of these ecosystems are located on very fragile landscape with very shallow soils. And then two, animals, when they make a lot of compaction, then whatever drop goes on it is likely to be eroded with the next rain. So here, these rangeland need a lot of attention, and I think people need to, if we really need to build biomass on them, there is need somehow or the other, one way or the other, to integrate some leguminous trees or other trees which can actually provide more shade and improve the overall above ground productivity. Then Kobusinge asked, what about the effect of pest and disease on productivity? As I said, of course, pests and diseases are very, very key in determining productivity. But during this study, we couldn't separate the effect of pests and diseases in the data we have. And generating some of this information with incidence incidence of disease and pest was a bit complicated. But if anyone has an idea on how to do it, that will be welcomed. Then we have Bizimana. Bizimana asked, most of the data is at global scale. This can hide a lot of details, especially in varying landscape and whatever, in countries like Rwanda. So is it possible to emphasize on using local data to improve the accuracy of the model? Bizimana is completely right. We need high resolution information. The good thing that the model which generates accommodates all type of images. So if you have Iconos, you have OrbView, you have Landsat, or you have Sentinel, all these will be accommodated by the model. So it's up to you now. If you want to improve what you have in Rwanda, there is no problem. The model is already built, and you can just test it on the model, on the data you have. Kobusinge Judith still asks, how was the model validated? Yes, the model was validated using, as I said, for productivity, we actually use the FAO inherent potential for soil, and for above ground, we use the proxy approach, where one part of the data was used for generating the model and the second part was used for validation. Then he said, it will be more accurate if we also put in the nutrient deposition, wet and dry deposition. Very well, right? But the issue here again is to get the information about wet and dry deposition. This is very, very important because nutrient loading through the atmospheric deposition is very, very important, especially for areas near the water bodies and the forest. As I said, we couldn't get data on dry deposition. The few stations which have used, which are generated some wet depositions, I think was during LAVEMP 1 for the Lake Victoria catchment, and that was in 2002, if I have good memory, with Mr. Wejuli at that time. Most of the studies on wet depositions are done basically in the south. I think Bootsman and Heki have done a very, very, very good work in those catchments. But in the area where we are, very, very few studies have been conducted. And that's why we didn't use them in the model. Yeah, so I need to also add one thing that in the validation process, of course, the model was shared with the member countries, and colleagues in the member countries also assisted to validate the output of the model. Okay, so Bizimana Jean-Pierre, you will get the presentation. We also appreciate your appreciation of our presentation. So if there is any additional question, I'm still ready to provide any insight if there is.
Hello? Is everything okay? All is well, dear participants?
Yeah, the presentation was very, very interesting. We appreciate too much.
Well, thank you, Jean-Pierre.
Oh, thank you, Margaret. How are you?
Fine, thank you. How are you?
I'm fine.
Few minutes.
So I don't know whether Prof, we can do anything in these remaining 30 minutes, or I don't know.
So yes, now I was suggesting that we take them through, or we give them an assignment for people to do at home, just to get a feel of what this making an estimation of the soil productivity index. Then tomorrow we could also do the same to show maybe tomorrow, after tomorrow, I think it's a program of after tomorrow, we should be able to actually show how it was done to make an estimate of the above ground productivity. So I think there is a link showing the data which was used, and there is also a link to the manual which was used, generated to actually estimate productivity. I just wanted to share some of this data and show how this was done in a few minutes, and then we will allow people to also do it at their ease.
Yeah, you're welcome, Professor. Please go ahead.
Okay.
Thank you.
Okay, so they have an Excel sheet called Soil Target Region. Soil Target Region. So I want to get to that data set. So this soil target region has, let me remove the filter.
Prof, can I direct them where it is?
Yeah, please.
Yeah,
go
dear
ahead,
participants, this was posted on your emails. Kindly check your emails. This is where this data, the file is, sorry. So please check it and go by the instructions. Thank you.
Yeah, thank you, Chair. So if you look at, if you manage to open it, this is basically the sheet or the table which is on the soil map of the data which is going to be used for soil productivity estimation. And here we just want to demonstrate how this was done in Excel how it's done in Excel, and then how the software or the tool which was generated in QGIS basically perform. What are the logic in the calculation? So you will actually see in this Excel sheet. So you have the name of the country. You have the FAO soil classification, the code. You have the code of the country. And then you have the area for that unit. I've removed for specific reason, I've removed the water bodies where we never had properties, just to make sure that you do at ease the calculation. Then you realize that this Excel has sand, it has silt, and it has clay. So those three elements give you the soil texture. So we have already provided the soil texture, but if you want to know how that one is done, we can share with you the Taylor triangle, or we can actually share with you the soil and water conservation tool, which assists you to define which texture class you have based on the three particle size. Then you have pH, and then you have another pH. You see pH water and pH water S. The pH water S is for the subsoil. And then you have pH water, should have been pH water T or topsoil, to mean for the topsoil. So you have, for each of these parameters, organic carbon, you have organic carbon for top and subsoil. The nitrogen you have for top and subsoil. You have base saturation for top and subsoil. So every parameter you have here, there is top and subsoil for all of them. Okay, so then we also added the name of the unit based on the FAO classification. And then we also added the productivity of that unit based on the FAO classification. Okay, and then you have the depth of the soil. Now, so this is the data set you are supposed to use. Now, I want also to share with you, just moving through it, the estimation of soil productivity in Excel and in the software. So I'm going to share with you this one. Let me stop sharing this, the Excel, and share the estimation. So basically, as you see, as we put as a learning outcome, is for people to use the concept of factor rating. For those who have been have used suitability assessment, certainly will not. They will understand easily this approach. but the aim is basically to have an idea of how the model has been, what is behind the model anyway. So we have put, just as for you to exercise 5 parameters out of the 7. And we also put the way you are supposed to do it. For example, if the idea is you want to use CEC as a parameter, the first thing, because we want you to do it for your country, so it is important that you filter among all the countries, filter your country. Once you filter your country, the next thing is how do we apply the factor rating? And then for you to apply the factor rating, you need to create a column for the factor rating CEC, and then use the formula if, which is provided in the PowerPoint. So this formula actually takes into consideration the different factor rating we have. For example, here for CEC, we are saying low means less than 5. And that's what, for example, if your cell is, the new cell is AP you have created, so you call it A. A meaning the factor rating for CEC, cation exchange capacity. Then on AP2, so AP1 will be A, AP2 will be the first cell where the formula has to be put. So you will copy this formula, you can actually copy it the way it is and change the location based on the location of the CEC. So once you have copied it and you say enter, it will give you, it will tell you if it is low or if it is moderate, or if it is high, or if it is very high. And then you copy that formula for the entire Excel, the entire column. You go to the next. For organic matter, you do the same. You go to the next, you do the same until you have the 5 done, and then you can combine them. You can combine them by using the formula which is there of LPI, which is equal to 100 times the square root of the product of the different factor rating you will get. So the number of zeros you are going to divide with should be 2 times the number of factors you have used. If you have 5 factors, then you should divide by 10 power 10. If you have 7 factors, you should divide by 10 power 10 power 14. Okay. So once that one is done, then you can now do the same way we did, use the same formula if by using these values, the range we have provided to get the last class for your classification. So we say very low, less than 30, low between 30 and 50, moderate between 50 and 70, high between 70 and 85, and very high above 85. So once that one is done, then you answer for us these questions. You compare the inherent productivity, which we have provided for you in the column AN, with what we have computed. And we will want you to estimate the percentage area covered by each LPI. So once you have your LPI, we want you to suggest some strategies to enhance agricultural production in your country. So that's what we will want you to do today, and tomorrow we will take some 10 minutes, 10 to 30 minutes to go through it together. For those who will fail to do it. But since they have created a link, if you have any question, don't hesitate. Even if it is midnight, send a message. I should be able to guide you. If there is any question, please, you are free to ask it.
Question, sir.
Yeah, go ahead, please.
The assignment will be submitted.
Not necessary, but it's good that you have it so that you can compare with what you do. It's good for learning.
Thank you.
Yeah, thank you very much, Prof.
Yes, Chair.
For opening doors for more questions. Dear participants, you can put, or in case of any issues or questions, please don't hesitate to punch them in the classroom, Google Classroom. Prof is already there, and other facilitators will also be able to address them. A lot of questions are coming up, requesting for the presentation, the slides, and the recording. Yes, the link to the recording will be shared with you. And then the PowerPoint presentation for Prof will also be shared as soon as possible. Requesting that we take up this assignment, dear participants. Let's take it up and come back with results tomorrow. And we compare and we see, and we learn. This is a way of proving that, yes, I think I've learned. Yes, I think I can do this one for my country. Yeah, and even for my whatever institution or whatever it may be. Yes, we have evaluation forms that will be filled in. Feel free to evaluate us and help us improve where we can. Prof has promised to be with us in the morning. In the tomorrow at the beginning of the live session. So kindly, participants, please take up the assignment, come with questions, come with concerns, where it hasn't worked and how it has not worked. He will be able to address them. Is there anything that we need to address? Yes.
There are some questions. I want to address them. One is coming from Mohammed Abegaz. He said controls of cation exchange capacity increase during the composting process. Does the specific surface area play a role? Yes. For those who have done soil chemistry, of course, they actually know the specific surface area is very, very important, especially in those interactions. The other one is Ahmed. Yeah, Emmanuel, I think, thank you very much, Emmanuel, for the compliment, and other people who have actually complimented us. For Kalumba, what depths were the sample taken? Kalumba, this is not our data, this is the global data. You can get it from FAO, but generally the topsoil is 0 to 15 centimeters, and the subsoils is between 15 and 30 centimeters. Polycarp, yes, we will share this. Thank you, Fabien, for your compliment. Thank you, Mugeni, for your compliment also. Irene, don't worry, things will be shared, including the assignment